Our second set of problems has to do with collision theory. Collision theory is described simply by just how the molecules are moving, but graphs are very common in kinetics, maybe more common than any other unit. So, really understanding those and connecting them with all parts of our understanding of kinetics and reaction rate is important. So, just to see and hear it another time, a Maxwell Boltzmann distribution curve, named after two different people, um, shows us the fraction or number of molecules moving with a certain speed or kinetic energy. The farther they are to the right, the higher the energy those particles have. The farther to the left, obviously, they'd be moving more slowly. The taller our graph is showing us that there's more molecules with that energy. So T1, we have a lot of molecules with this energy. T2, we have a lot of molecules with this energy. And obviously, I drew in T3 as I answered the question. T3 is a little bit sloppy, but for all curves, if we're looking at the same sample, they should have the same area under the curve. So if it gets steeper, it has to get smushed together in general, or if it's taller. And as we move farther to the right, it would have to get flatter. So right here, which line represents a higher temperature? Justify it. It's T2 because a larger number of the molecules are farther to the right. Right there, we have a whole bunch with this much energy. We have a whole bunch with this much energy. But in both cases, a few of the molecules are moving slow. It's kind of an average distribution here. We can think of it as a statistical bell curve. And these two gentlemen actually did a lot of the proof of statistical mechanics related to chemistry and physics. But as we go to the right, T2 is constantly higher in terms of the number of particles at that higher energy. The third line that I drew is showing that we have a higher temperature. And then why would it increase the reaction rate in terms of the graphs and kinetic or collision theory? In terms of the graphs, there's a vertical line right there that's labeled the activation energy. Only the small fraction under the blue line can react at temperature 1. The larger fraction under the red line can react at temperature 2. And this whole chunk right here could react at temperature 3. More particles beyond the activation energy. But that's only thinking about it in terms of what the graph's showing us. In terms of collision theory, we have a higher percentage of particles moving faster. They are colliding with one another. We also remember both parts of this more often and with more energy. Both of those are more likely to make our collision successful. If we added a catalyst that doesn't heat anything up, it doesn't change any of our temperatures, but what it does is it changes where the activation energy barrier is. It would move that barrier to the left so that a higher percentage from 1, 2, 3, all three temperatures are able to react. And then right here, just good reading of graphs. How much faster is T2 than T1? We don't know what the temperatures are. We don't know what the reaction is, but there's about, and not exactly, but almost twice as much under the curve for T2 compared to T1. B is related to this graph right here, and I'm kind of treating A and B as NO2 and CO, and C and D as CO2 and NO. We've got an uphill, we've got a downhill, and we've got some values. The activation energy is the energy hill we have to get over. So yes, we have to get up to 100, but we already start with a certain amount of potential energy. So it's just that increase. If we thought about what was happening during the process, kind of going back to the picture that was in the previous one with NO and O3, we have to get one of these oxygens off of the N and get it onto the C. So I pictured it as, well, O was bonded to N, which was bonded to O, but then that O is going to be bonded to C, which will be bonded to O. So it's breaking away from the N and it's bonding to the C. Sometimes it's obvious and easy to estimate or explain the activated complex, but more often than not, it is not. If we were thinking still in terms of the graph and a catalyst, the catalyst would once again lower the hill. In terms of collision theory, that doesn't change the energy of our reactants nor our products. It doesn't make our particles move faster, but it does mean that a collision with less than 60 kilojoules of energy per mole would become a successful collision that would result in reactants turning into products. And if we were changing the CO, how would that change the graph? Remember, CO is one of our reactants, so I'd put more of it there. That doesn't necessarily make it have more energy. That doesn't make it hotter. That doesn't lower the hill. It doesn't change the graph. The starting energy and ending energy are determined by what our reactants are. The activation energy is determined by the breaking and making of the bonds. But a higher concentration of a chemical would mean more total collisions, and it would be more likely we'd have a successful collision. It would go faster, but that doesn't change our activation energy, our temperature, or our graph.